Welcome to Lesson 11D, Comments about the Theta-Beta-M relationship. In this lesson, we'll provide some qualitative comments about the Theta-Beta-M relationship. Then we'll compare strong versus weak oblique shocks and downstream Mach number behavior. Now I'll make some comments about the Theta-Beta-M plot. First, there is a unique curve for any M1 greater than 1. Where you can't have a shock unless M1 is between 1 and infinity. All of these curves intersect at theta equals 0 and beta equal 90 degrees, where for a typical oblique shock, beta is the shock angle and theta is the turning angle as discussed previously. When beta equal 90 degrees, you see that theta equals 0 because this is a normal shock. And for any Mach number between 1 and infinity, we can have a normal shock. That's why all the curves intersect at theta equals 0 and beta equal 90. This is the strongest possible shock, namely the normal shock. For a given M1, at any beta less than 90 degrees, the shock is weaker than the normal shock. So quantities like pressure jump, temperature jump would be smaller across this oblique shock than they would be across the normal shock for the same Mach number. Beta cannot go to 0 degrees unless M1 goes to infinity. This is what we showed here. The minimum beta keeps decreasing until we hit 0 when Mach number goes to infinity. So a corollary to this comment is that beta-min decreases as M1 increases. What does beta equal 0 even mean? As beta gets smaller and smaller, the shock gets shallower and shallower, and at m equal infinity, the shock theoretically becomes parallel to the flow, which of course is impossible, but this is a theoretical limit. For a given M1, theta equals 0 at some minimum beta, which as we already said, is equivalent to the Mach angle. This is the case of an isentropic Mach wave. The opposite extreme is that theta equals 0 at beta equal 90 degrees, which is the normal shock case. For beta between mu, its minimum, and 90 degrees, theta reaches a maximum at some beta. We'll call this theta max. And furthermore, theta max increases as M1 increases. We see this in the red line on the plot, where I connected points of maximum theta. Everything to the right of this red line is called a strong shock, and everything to the left is called a weak oblique shock, which we'll discuss in more detail later. Above theta max, an oblique shock cannot exist. In other words, the flow cannot turn that sharply. If this is theta max for a given Mach number, it is impossible to turn the flow any more than this. We can also say that below beta-min, an oblique shock cannot exist at the associated Mach number. Mathematically, equation 9 can yield negative values of theta, but we will ignore these since they're not possible. In other words, you can't have an oblique shock at some beta and some M1 where the flow turns at some negative theta. This is impossible. The Theta-Beta-M equation is explicit for theta, as we've already stated. Theta is unique for a given beta, M1, and gamma. Unfortunately, we usually know theta and M1 and want to predict beta. But the Theta-Beta-M equation is implicit when you want to find beta as a function of theta, M1, and gamma. So either iteration or some sophisticated software is necessary to solve for beta. To make matters worse, for a given theta, where theta is less than theta max, and Mach number M1, there are two possible betas. On our Theta-Beta-M plot, if we have a given theta and some m, suppose for example we're at 20 degrees theta and M1 is 3, I get a beta there and another beta there. One to the right of theta max and one to the left of theta max. We identify these as the strong oblique shock to the right and the one to the left as the weak oblique shock, which I also sketch here. Any beta to the left of theta max is a weak oblique shock, and any beta to the right of theta equal theta max is a strong oblique shock.
How can you tell which one it will be, weak or strong?
Great question, Harry. The answer is a little vague. The weak one is preferred and more common. The strong one must have very high downstream pressure to form. As I said, this answer is rather vague and not very satisfying.
so we don't really know the answer unless we analyze the entire flow. Consider, for example, flow approaching some solid body at supersonic speeds. We get a bow shock. This shock is normal right at the center line, so beta is 90 degrees or beta max at the center line. Some small distance away from the center line, beta is less than 90 degrees, but this is a strong oblique shock. And at this point, beta may become small enough to be a weak oblique shock. Depending on all the parameters in our problem, I may not have reached that point yet in this sketch. I'll discuss the details of a bow shock later in the semester. By the way, for a given Mach number, the bigger the beta, the stronger the shock, and the strongest possible shock is the normal shock where beta equals 90 degrees. We also see this dashed green line, or curve. This is called the sonic line, or sonic curve. As indicated here, everything to the left of this green line has a supersonic Mach number 2, while everything to the right of this line has a subsonic Mach number after the shock. So M2 equal 1 along this green dashed line, the sonic line. I'll write some comments here. To the left of M2 equal 1, M2 is greater than 1, since the shock is weak. In other words, M2 does not differ much from M1. So zone 2 after the shock is supersonic, where 1 and 2 are before and after the shock as usual. To the right of this sonic line, M2 is less than 1, so 2 is subsonic, since the shock is stronger, and M2 differs a lot from M1. It would be nice if the green and red lines coincided. In other words, the strong and weak division would be the same as the sonic division. But that's not how it is. In fact, there's this region, or zone, that I'll call the strange zone, between the green and the red curves, where you can have a weak shock, but the Mach number after the shock is still subsonic. I'll write that here. In the strange zone, the oblique shock is weak, but M2 is subsonic, which behaves more like a strong shock. So unfortunately, because of this strange zone, we can write this. For all strong oblique shocks, M2 is less than 1. And for most weak oblique shocks, M2 is greater than 1, where we have to use the word most, because this is true except in the strange zone.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.